He's going to present TOCTOU, a network attestation approach, and let's hear more about this work from Will himself. All yours.
Hi everyone, my name is Pavel, and I'm going to be presenting Train TOCTOU Resilient Attestation for IoT networks. Train is a hybrid network attestation scheme. It minimizes TOCTOU vulnerabilities in IoT networks by enabling fast, synchronized attestation across many devices, even in the presence of compromised nodes. Embedded IoT and cyber physical systems have become frequent targets for real-world attacks. Stuxnet, Mirai, the Ukraine power grid attack all show how these systems can be hijacked, disrupted, or damaged. Protecting embedded and IoT devices, especially in safety-critical settings, is more important than ever before. In our work, we focus on low-end embedded systems, embedded devices, which are common in safety-critical IoT networks. These devices typically operate with a single core, running a single process directly on bare metal. They lack any kind of memory protection, and they have minimal computational resources. Remote attestation is a security mechanism that allows a trusted verifier to remotely assess the integrity of a potentially compromised device called the prover. This is typically realized as a challenge and response protocol, where the verifier sends a cryptographic challenge to the prover, which then computes an attestation report, which is typically a keyed MAC over its software state as well as the challenge, which it then returns to the verifier, and then the verifier validates the report to determine whether the prover is in a compromise or is in an expected benign state. Network attestation extends remote attestation into many interconnected provers. The verifier initiates requests that propagate throughout the network. Each prover attests its own state and forwards the request onwards. Existing work in network attestation does have several important challenges, such as high runtime overhead for remote attestation. Attestation requires each device to compute a cryptographic report, which can be slow and low-end hardware, or in heterogeneous environments, devices may have very different computational capabilities, leading to inconsistent and high latency during attestation. Unreliable communication, networks may suffer from message loss, delays, or active interference by compromised provers. And TOCTOU vulnerabilities. TOCTOU stands for time of check to time of use. It's a class of vulnerability that typically refers to a window between when a system checks a condition and when it acts on that condition. For this work, we worry about two flavors of TOCTOU vulnerabilities. TOCTOU RA, which occurs across time on a single device, and TOCTOU NA, which occurs across the devices in a network. TOCTOU RA refers to the time window between two successive remote attestations on the same device. For example, the verifier will request an attestation, and then the device will perform attestation and respond as benign. Then malware will infect it, does its damage, deletes itself, all before the next attestation. And as a result, with the next attestation, it will say it's benign, and then the verifier will incorrectly believe that device was benign throughout. TOCTOU NA refers to a time difference between attestations across different devices in the network. In short, so we have an example here of a visualization here where the verifier will send out the report to the network, and at time 1, device A will receive the report and perform its attestation. At time 2, device B still hasn't received the report. At time 3, the device A is now compromised. At time 4, device B finally gets the attestation request due to some network latency. And then at time 5, the verifier has all of the reports, and it will erroneously conclude that the network was benign at time equals 5. Train addresses both types of TOCTOU vulnerabilities. To address TOCTOU RA, we rely on prior work, Rata and Kasu, both of which provide lightweight security mechanisms that either actively or passively address TOCTOU RA, and I'll describe these in the next slides. And to minimize TOCTOU NA, we coordinate remote attestation across the entire network, ensuring that all devices perform attestation nearly simultaneously. Rata is a passive hardware root of trust. It detects TOCTOU attacks by securely recording the last modification time of program memory. So instead of attesting the entire PMEM region, all we have to do is indirectly attest the software state by just attesting the value of this last modification time, which will result in minimal overhead on remote attestation. And Kasu is an active hardware root of trust, which entirely prevents TOCTOU RA attacks by enforcing runtime immutability of program memory. So any unauthorized modification will trigger an immediate reset, and the PMEM can only be modified through a secure update mechanism. At that point, the device just needs to send a lightweight heartbeat about the same size as the LMT to prove it is alive. Garota is an additional hardware modification that guarantees the triggering of trusted tasks based on hardware events such as timers or network activity. Guaranteed triggering is enforced by hardware, ensuring that these events always generate an interrupt. Even if the devices are set due to malware or any other kind of failure, Garota ensures that trusted tasks are the first to execute upon reboot, guaranteeing re-triggering. We also use hash chains for one-to-many authentication. This is a concept that goes back to Leslie Lamport's original works. If you're not familiar with hash chains, you can just think of it as signing every message, but instead of an expensive cryptographic signature, you just compute a single hash, and this provides lightweight, scalable authentication for the network. Train supports two architectural variants. Train A, which assumes provers have real-time clocks. This enables precise network synchronized attestation across all provers. And Train B, which does not require real-time clocks. Instead, it estimates timing based on each prover's height in the spanning tree of the network. Provers must support either RATA or CASU. We assume that the network is connected in quasi-static during attestation, and each prover includes a small trusted computing base based off of NetTCB and timer TCB from Garota. These components are hardware enforced and guaranteed to run even in the presence of malware or competing software. Network and timer events always take top priority, ensuring that attestation messages are prioritized and that attestation remains synchronized across all devices in the network. And we also assume that the verifier is trusted and computationally capable. The role of the verifier in Train is to coordinate the attestation process across the network. It initiates attestation requests, verifies attestation reports, and maintains the overall state of the attestation session. While each prover is responsible for verifying incoming attestation requests, performing its own attestation, and forwarding requests and reports to its neighbors. The verifier begins the process by composing an attestation request, where send is the sender device's ID, new hash and new hash in that are used for authentication, and t-attest is the attestation timer, setting a timeout for responses, and it initializes a list of provers to track during the attestation process. Each prover will discard any incoming attestation reports, and it will wait to receive an attestation request. Upon receiving a valid attestation request, the prover verifies the request authenticity using the hash chain and checks that the requested attestation time aligns with its local real-time clock. If the validation passes, the prover accepts the attestation request and proceeds. Once verified, the prover modifies the sender field in the request and broadcasts the request to its neighbors. It then sets a local timer based on its real-time clock to trigger attestation at the designated time. While waiting for the attestation timer to expire, the prover continues normal operation. This is safe because of timer TCB, which ensures that the attestation will still be executed at the correct time, even if the device is busy with other tasks. Any new attestation requests or replies received during this period are discarded to prevent concurrent attestation sessions from interfering. When the timer expires, the prover's perform its attestation. It computes an authenticated attestation report, which is a keyed MAC over its current LMT and associated metadata in the case of RATA, or a keyed MAC over the challenge and metadata in the case of CASU. And it records the exact time the attestation was performed. After completing attestation, the prover will send its report up to its parent. It will set up a forwarding timer, and it will continue normal operation, forwarding any child attestation reports it receives to its parent. Importantly, thanks to NetTCB, even if a device is compromised, the forwarding of attestation messages is still guaranteed. NetTCB ensures that attestation traffic is prioritized and reliably propagated upward through the network. Finally, the verifier verifies all of the attestation reports received within the timeout window. It outputs 3 sets: devices that did not successfully attest, devices that successfully attested, and devices that did not respond. And we evaluated Train in a simulated environment using OMNet++. This is similar to what all other network attestation schemes use. We simulated it with different topologies and up to 1 million different prover devices, as well as realistic communication delays. And our results show that Train remains efficient and scalable even at very large or small network sizes, with all different sorts of topologies as well. We also measure Train's runtime and energy overhead. The attestation verification takes about 13 milliseconds, which is the hash chain verification, and actual report generating with hashing our LMT, that takes about 30 milliseconds. And compared to other schemes, this is a lot faster because they're attesting the entire state of the memory compared to our small region. The hardware overhead of power is only about 2% compared to Rata or Kasu. And we prototype train atop OpenMSP 430, which is a 16-bit open source microcontroller synthesized for FPGAs. The required hardware modifications are minimal. We're mainly just adding net TCB and timer TCB components from Garota for the network and timer guarantees. For resource overhead, Train Kasu adds less than 0.5% more LUTs and the registers compared to regular Kasu, while Train Rata adds even less. So Train achieves TOCTOU resilience with under 1% hardware overhead, which is really good for these resource-constrained deployments. And Train is a TOCTOU resilient network attestation protocol that's tailored for low-end devices. We offer 2 variants, Train A, which uses real-time clocks to start attestation simultaneously across the network, and Train B, which uses spanning tree height to approximate synchronized attestation when clocks are unavailable. Train can be instantiated with either Rata combined with Garota, providing passive detection, or Kasu combined with Garota, providing active prevention. Our evaluation shows that Train achieves efficient, scalable network attestation with low runtime energy and hardware overhead, and Train is open source and available at the link shown here below. And then here's also a picture of it running on some FPGAs.
Great, thank you. Any questions? So while we're thinking, I have a question. In one of your evaluation, the number of devices you showed were in the order of thousands.
Yeah.
And I noticed that the provers and verifiers all need to maintain some sort of their own local time. And then in turn, that needs to be synchronized. So how do you balance all of that? Because and then of course you're using RTC or real-time clocks, but then with these millions and thousands of devices, how do you manage time sync, especially on the resource-constrained devices? That's my first question. And then your other one is that you rely on some kind of topology, if not time.
Yep.
That's also pretty resource intensive. So how do you, what's the trade-off there? How do you manage
Sure,
that?
yeah, I mean, the trade-off for real-time clocks versus no real-time clocks is cost for the most part, right? It's not a super expensive component, but it is expensive relative to the cost of these devices. So that's why we created the Train A and Train B variants. For managing the actual synchronization and the topology discovery, we refer to existing topology discovery algorithms and all of that. So that's slightly outside of the scope of us.
And how about the cost of time sync?
The cost of time sync, we have that during the provisioning stage, so it's not happening during the attestation.
Time sync is something that happens periodically because the time drifts away.
Sure.
And so then it should happen online as well later.
That can be added as a separate component, which will be separate from the attestation process.
Okay, thank you. Any other questions? If not, let's thank our speaker.